atomic clocks. And an atomic clock, this is a classic atomic clock. This is a cesium beam clock. It's a type of clock that's used in reference clocks in television stations, in banks, yes, they do time everything, and all over the world. And banks of them are used together to create what we usually refer to as universal coordinated time. They're known as primary standards, and they don't vary very much at all. So what is an atomic clock? Well, it's atomic, but it's not atomic like this. This is actually, physicists call this nuclear, and an atomic clock is an atomic device. But they do share a same heritage in that they came about at roughly the same time back in the late 40s. Now, in DSAC, we use a mercury trap clock, and I'm going to tell you about that just a little bit. There are other types of atomic clocks, but the principle is reasonably the same, even though the details are immensely more complex depending on the different ones. But we use a mercury atom here. Okay, it's got 80 electrons spinning around it in all these little shells. But the one we care about is actually the two on the outside shell, because those are the ones that we interact with. And we ionize these, which means we use an electric current to knock off one of the electrons. So then we only worry about the one. And we call this mercury atom and this electron up here, we refer to it as a quantum tuning fork. It will respond to certain radio signals, but only certain ones, the same way a tuning fork only vibrates at one frequency. So this is our little tuning fork. And what we do is we send a radio frequency at this atom, and this radio frequency interacts with the electron. And if the frequency is not right, the tuning fork doesn't do anything. So the atom is not perturbed. If the frequency is a little faster, in my example, then it will vibrate with it. Now, it's not actually vibrating, it's actually doing a magnetic pole nuclear balance spin thing, and it's all sorts of physics. But this frequency, if it's exactly 40.5 and about 50 decimal points frequency, this atom will react in a way that we can then measure with the ultraviolet light. Now, one of the difficulties with all atomic clocks is these atoms are also not just affected by the frequency you're hitting them with, they're affected by the world around them. And so we try to, I like to say, we try to disconnect them from the universe. And we do that by trapping them. And so we put them inside of this little device, which is about the size of a Three Musketeers bar. Okay, it's the big bar, not the little bite-sized one. And we basically, inside of these gold rods here, we form an electric field and we put a bunch of mercury atoms in there. We ionize them, and they all stay in a little bottle. So they're in this little bottle. So they don't interact with any of the metal. They don't bounce off of anything. They just kind of fly around in lazy circles. And those lazy circles make them very calm, okay? And when they're very calm, they can react very nicely to our radio waves that we pump into these ports here, okay? Now, you might think, okay, it's mercury. Is this thing dangerous? It's not like a Snickers bar. Well, I mean, a Three Musketeers, which is dangerous in its own way, right? But the amount of mercury we actually have inside of our tube, there's more mercury in 2 cans of tuna fish. So there's only about 100,000 atoms of mercury inside of our tube, which is a very, very small amount of mercury. And it's a very precise way. It takes months to get the balance just right in the mercury as we build up these clocks. So now Todd was talking about how in the DSN we use these atomic clocks. And you may have heard recently NIST, the National Institute of Standards and Technology, they're sort of the United States keeper of time. They have a clock called NIST F1. And it's the most accurate clock in the world right now. You know, it's sort of like who's the best quarterback. It's always flipping around between different organizations. But this thing is the size of a kitchen. In fact, it's the size of an industrial kitchen, okay? And, but it is quite accurate. It's a different technology than we use. That's where they throw the atoms up in the air and they let them come down. And while they're coming down, they're not connected to anything, and they measure them that way. And that's what this big column's for. But our technology has been used in the DSN, and these things, they're called LITs. It stands for linear ion trap something. And And it's about the size of a refrigerator. Now this is a fancy refrigerator. Each one of these is the size of a regular refrigerator. But you get the idea, from a kitchen to a refrigerator to DSAC, which is about the size of a toaster oven. I could literally hold it right here, and it's not all that heavy either. And that's the thing that this project has been doing, is we've been taking a technology that's been in the works and been deployed in the DSN for the last 5 to 10 years, and it's been in the works for even longer. And we've been shrinking it down so that we can put it on a spacecraft and use it in space the way that Todd has been talking about. Now, one of the key aspects of a technology demonstration mission, it's a little different than the normal type of mission that JPL does. Our goal is not to go to a certain place and collect science about a certain target, as we call it. It's to test this clock in the environment of space and on a spacecraft and see how well it works and to see where the warts are, so that we can then design the real one to go to Jupiter or to Mars or to another planet. And these technology demonstration missions are a new class of missions that NASA's been doing for about the last 4 years, where we're building this payload. So there's our little clock, there's the USO that Todd showed you earlier, and then this is a measurement device. It's a GPS receiver that we use to measure the clock in space. And we put it on a small spacecraft. This spacecraft is about the size of this podium. So it's very small compared to normal JPL spacecraft that would reach to the ceiling here. And we fly that spacecraft with a bunch of other spacecraft on a mission that the Air Force is running. Now, when I was a kid, I used to play Monopoly with my sisters. And you're sitting there and you've got Baltic Avenue and you want North Carolina Avenue, and your sister's got it, so you offer her, a railroad and Baltic and maybe a little bit of cash to sweeten the deal. But my other sister wants that too, so we work out like this three-way deal where there's all this money and property changing hands. Well, that's the way we get onto these missions in a way. What happens is, Surrey, which is a United States satellite provider, has a mission where they want to fly a lot of demonstration payloads. So we're paying them for a seat on their spacecraft. It's sort of like buying an airline ticket. We didn't buy the spacecraft, we're just buying a spot on it. And they've got some other payloads. And then we're also paying for 2 Air Force payloads to be on this spacecraft, so that the Air Force will turn around and give us a ride on their rocket. So we start trading things around, and it makes for a very interesting and complex arrangement, but it also saves the taxpayers a whole lot of money, because we're not paying anything at all for this rocket. The Air Force is flying this rocket for another reason, and all of these satellites that are on this rocket are sort of getting a free ride because the Air Force wants to check this out. This is a Falcon Heavy, by the way, which is the next version of the Falcon 9 that SpaceX is planning to fly later this year for the first time. And it's basically 3 Falcon 9s tied together. So it's a very powerful rocket, and the Air Force is wanting to check it out, so we get to ride pretty much for free just for carrying a couple of their other little payloads. So that's sort of how we work these deals out. So I think I'm going to hand it back over to Todd here. He's going to switch back now to what we do with the clock in some fancy ways.
Thanks, Alan.
Oh, you're going to describe the mission.
Yeah.
That's right.
So the rocket puts us in space. It's a low Earth orbit on board that Surrey spacecraft that Alan talked about. We're scheduled currently to launch September 2016, but things move, and so we'll see if that's the date that we actually fly. But once we are in space, Surrey obviously needs to check out its spacecraft for a few weeks, and then they turn us on for about a month. And then after that month, we've checked out DSAC. We think it's working okay. We're ready to start our nominal mission, and that's about 5 months long. And the way in which we're going to operate our mission is that receiver that Alan talked about is going to receive GPS signals from the InView constellation. So this spacecraft is in about a 700-kilometer orbit. The GPS satellites are at about a 20,000-kilometer orbit. We see a lot of GPS satellites. We see on average about 12 in view continuously. That's a lot of data. And it's fair to ask, okay, DSAC, you're a new type of atomic clock. You just said GPS has atomic clocks. DSAC's supposed to be better than those atomic clocks. How's that going to work? Well, it turns out that there are over 400 tracking stations on Earth tracking the GPS constellation all the time. And those tracking stations have determined the location of each satellite continuously to about 2 centimeters. and the clock on board that satellite to about 50 picoseconds. So even though the GPS clock isn't as stable as our clock, it's moving around, we know how it's moving around. We can take that information with these measurements, and we can determine how well our clock operates. And so our requirement is to show that DSAC stability is better than 2 nanoseconds per day. And our goal is about 0.3 of a nanosecond per day. And if you remember back when I was talking about the DSN, it's about 1/10 of a nanosecond per day. So we're really in the ballpark of what the DSN is able to provide. And in fact, at these levels, other errors in those range and Doppler measurements start to dominate those measurements, and the clock error essentially goes away. And so with that, we're hoping to demonstrate DSAC's utility for future missions, show that it can navigate OTB quite well. And then after that first 5 months, we're not a big mission, and we're trying to do this as efficiently, and I don't want to say cheaply, but as economically as we can. And so we've got our data, and that's enough to validate the clock. Now what we're interested in is just making sure the thing still ticks, because for long life duration missions, you need to work for more than a year. We're only going to operate for a year, but theoretically we could operate longer as long as we keep paying the rent on the Surrey spacecraft. So, cool stuff. This is our demonstration clock. It's a prototype clock. It's not the final clock that would go on a future mission. What you would do next is, and what we're learning as part of our project, is how we would actually shrink this thing further. So this is about 9 inches by 10 inches by 11 inches. We've already got lots of ideas how to probably cut that by a quarter and make it about this big. And that's very reasonable to fly on future space missions. And so some of the ways in which we can use DSAC for future missions in the arena of science and navigation, let's talk about that a little bit. So here's an illustration of Cassini transmitting a signal through the rings and received here at the DSN. This is that one-way signal again, and what the Cassini has to use today are USOs. And USOs are great. You get a lot of data to probe the rings, but DSAC would be about 10 to 100 times more accurate than that measurement. And so we could learn a lot more about those rings if DSAC were on board Cassini. Places like Mars, spacecraft transmit signals through the atmosphere as the satellite rises and sets, and that signal gets affected by the atmosphere. And we can learn a lot about the atmosphere by measuring these signals. Again, this is a one-way signal, and so Mars orbiters have USOs, and that signal is received back here at the DSN, and the USO is the limiting error source. If DSAC were on board, that measurement would be 10 to 100 times more accurate. Other ways in which we can use DSAC is put DSAC on board an orbiter. Recall that little illustration I had earlier where those satellites were getting a lot of data almost continuously. Well, with DSAC, we could take advantage of that for an orbit around Mars. And using DSAC with all that data, and using the fact that we can downlink to the DSN at Ka band. So today, we traditionally use X band, which is about 8 gigahertz. Ka band is about 40-odd gigahertz. The data that we would get at Ka band is about 10 times more accurate than at X band. So if you double the data and you improve the data, we could start determining things like the gravity field, the long-term gravity field at Mars very accurately. One of the things that we learned recently is that there's a lot of ice mass redistributions over the course of a year, a Martian year. DSAC might be able to contribute to understanding that better. Other ways in which we can use DSAC is NASA is developing a spacecraft to explore Europa. It's a moon of Jupiter. Europa is encased in an ice shell, and all of our data says that there is an ocean underneath that ice. And one of the key things that this Europa flyby mission is going to do is probe the characteristics of the ice in the ocean underneath using a variety of instruments. And one of those investigations is going to involve determining the gravity field around Europa. And much like before, this example, we're probing the gravity field here.